This lesson will build on the fundamental definition of moments. We're going to explore in a little more detail how we break down the details of a question, how we turn words into maths, how we put all the information onto a diagram that we can then use, and what the most efficient way would be to interpret, make sense of, and then solve those problems. We're also going to look into what happens when something is on the point of no longer being in equilibrium. So what happens in the edge case where something's just about to not be in equilibrium, and what the different forces do, how we can make use of that. Let's begin with this example. We have a horizontal lever with a known mass modeled as uniform. We have a known length. We're going to put a large mass at one end, which is designed to be lifted by pushing down on the other end. A good idea as you're working through a question like this is to read through it once and try to make sense of the story. What's the big picture behind it? And then read through it again, start making a diagram. If necessary, then make a second draft of your diagram to make sure you've got all the forces you need and any information about distances that might be relevant. Remember, every force will have an arrow indicating what direction it's acting. And if you've got any relevant points, if they've not already been given labels by the question, like in this case A, B, and C, if there are any other points, give those labels as well. If there are some unknown forces, give them sensible names. And when you've done that, reread the question one more time to make sure you've not missed out any key information. In this particular case, the question is asking you to find the range of possible values of x, where x is the distance that a fulcrum will be placed. A fulcrum is basically the point at which the lever will pivot. So when you jam something against something else in order to leverage something up, the thing that holds the lever still, so that one end of it goes down and the other end goes up, the bit in between is called the fulcrum. Pause the video, have a go at interpreting this question, and then come back and see if your diagram matches mine. Okay, let's take a look at this question piece by piece. I'm going to start by color coding some key phrases within this question. To begin with, let's take a look at what we can say from the stuff in red. Horizontal lever, so we're going to draw ourselves a horizontal line. AB, so we label the ends A and B. The mass is 10 kilograms and it's a uniform rod of length 2 meters. That means that we can treat it as if all of the mass has its effect in the center of the rod. Uniform means it's going to be the same density throughout, so the material is equivalent on the left-hand side as it is on the right-hand side, and we can therefore say that the mass of 10 kilograms produces a weight of 10 g newtons, exactly 1 meter along. It also talks about a pivot, which is placed a certain distance from the point A, and a large mass that is placed at A. When you've got a lot of words, it's helpful to break this down and take it a sentence at a time. And as I said, if you need to redraw a diagram after you discover, oh, there's an extra piece that I've missed out, or I can't easily interpret that with the way I've currently got my diagram drawn, just redraw the diagram. So we should have initially something like this. We've got the force pulling down at M, which is going to be the middle, and that's the 10g, which is the weight. It's about 100 newtons, just less than 100 newtons, because it's going to be the mass of 10 kilograms multiplied by the acceleration due to gravity, which is 9.8 meters per second. And we're also told about the distance, so I'm going to put the distance from M to B, from the middle to one end, as 1 meter. And we are also given this 500 kilogram mass placed at A. So that's obviously going to be a significant weight pulling down, 500 g, about 5,000 newtons of force on that end. And in order to make it balance, it says that given that the force of 200 newtons is sufficient to make it tilt, find the range of possible values of x. From the initial diagram, it just says the lever pivots on a fulcrum positioned at C, a distance x meters from A, but the 500 kilogram mass is to be lifted by pushing directly down on the lever at B. So even reading that second sentence gives me enough information to indicate that there is a force at B. And then when we reach the later part of the question, we'll recognize that for a particular value of the force, we can work out exactly what the range of values for x would be given that it tilts. At this stage, we've indicated all the forces that were given. So the 10g is from the weight of the lever itself. The 500g is the weight of the 500 kilogram mass. And then F on the right is the pushing directly down force that was referred to in the second sentence. If these were the only forces acting, then the entire rod would be accelerating downwards because the only forces acting on it are downwards forces. So there must be some other force resisting that, and that's why we've got that vertical force at the point C. I've got a little inverted V or a triangle to indicate that this is a point on which the rod rests, and I'm going to use R as the reaction force, the normal reaction, which is going to be a force perpendicular to the surface or the direction of potential motion, because it's basically pushing directly up from the support or the pivot point, the fulcrum that's referred to in this question. We're also told in the next part the lever pivots at a distance x meters from A, so we can include x. And if we've got x, we can also include 1 minus x. So now I've got all the distances and I've got all the forces. Then we get to the question part of the question. Because currently we've got F, R, and X are all unknowns. And unless we know what's happening or we have more information, we can't do a huge amount with this. But then they say that a force of 200 newtons is sufficient to cause the lever to tilt. That means we can replace the F acting at B with 200. The next bit we need to think about is perhaps double check, read through, convince yourself that everything in the question matches what we're expecting. Do we properly understand the question being asked? So this is about telling the story of the question. Sufficient to cause the lever to tilt. What does that actually mean? Well, it means if you push down with that 200 newtons at B, then the lever will no longer be in equilibrium. It's going to be twisting clockwise. B will move down, and the 500 kilogram mass that's at the far end is going to start moving upwards. Now, the range of possible values of x seems to suggest that there are a number of different possibilities. It might be that for very small values of x, one thing happens, and for larger values, the same sort of thing happens, but slightly differently. And there's probably a limit to how big or how small x can be. And you can make sense of that by asking yourself, if 200 newtons is only just enough to cause it to tilt, then what kind of value would I expect for x? And if 200 is more than enough to make it tilt, or much more than enough, so as soon as you push down with 200, it starts rotating more and more rapidly in the clockwise direction, then what kind of x values would that require? Another thing to notice here is the number of unknowns involved. We don't know r, and we don't know x. Now, r is a bit less important because we could ignore moments entirely and still find the value of r. That just comes from taking the vertical net force and recognizing that if the object is in equilibrium, that vertical net force will be 0. We could work out r directly from that. But more importantly, we could use moments to calculate something about x that doesn't involve r at all, as long as we choose where we take moments about more carefully. Now, the next thing I'm going to do is a crucial concept within a large number of mechanics questions. If something is about to slip down a slope, when we start looking at friction, we'll be talking about the moment when it's about to slip, because that's the sweet spot where there's enough force to cause it to slip, but it's perfectly balancing the maximum frictional force resisting it. In this case, if we look at when it's about to tilt, we'll be able to make sense of the sweet spot, the value of x where tilting is about to occur. It's like saying the boiling point of water is 100 degrees centigrade. Knowing that the boiling point is 100 means that if we heat water up to more than 100, we know it's going to have turned into steam by that point, and if less than 100, then it won't have done by then. Something like that. So the edge, the critical value, is what we're interested in. So let's look at what happens when the rod or the lever is about to tilt. Well, for a start, if it's about to tilt, but at this moment not tilting, it's in equilibrium. And that is the most useful thing we can have, because we can work with it when we've got equilibrium. We can, for instance, take moments about the point C. We can look at the point C, which is the fulcrum in this case. That's a useful place to take moments about, because there's no force acting, there's no moment caused by the force of R acting at C, because it's a distance of 0 away. So r is neither trying to twist it clockwise nor anti-clockwise, because it's not to the left or to the right of that pivot point. And that means that when we look at the forces that do cause a moment, we only need to look at the forces that we actually know the value of. There's the 500G, there's the 10G, and there's the 200. And as long as we make sense of which of those are pulling which way, we can create our equation. should look something like this. The 200 from all the way at the far end at B is a total distance of 2 minus x meters away. The 10G, that still has some effect, so it's 100 newtons. It's not completely insignificant. We need to take it into account. The weight of the lever itself effectively is doing some of the work, and that's a distance of 1 minus x away. Both of those forces are pulling down on the right of the pivot, so they are having an effect which is going to attempt at least to turn the lever clockwise, to bring the right hand side down and the left hand side up. So resisting that is the effect of the 500 kilogram mass, which has a 500 G weight. So the force is 500 G and the distance is x. So that force on that side is pulling down on the left. It's attempting to twist the whole thing anti-clockwise. That equation is enough to find x. It still looks a bit messy, but we can expand things out. We can simplify, we can rearrange. We basically, after we've got rid of all the brackets and tidied things up, we want to put anything involving x on the same side of the equation, and then we can take out x as a common factor. And as soon as we've done that, well, we can chuck it all in the calculator and get a value. Now, interpreting this value is really important as well. Remember that the wording of the question was 200 newtons is sufficient to cause it to tilt, which actually means at 200 newtons, the object is not in equilibrium anymore. We've just found the value of x that would cause it to be in equilibrium. We get a lot of leverage. If you think about it, 0.096 meters, that's approximately 10 centimeters. So we've got a 2 meter lever and we've wedged it onto something 10 centimeters away from the large thing we're trying to lift. So we've shoved the crowbar under an engine block or whatever it might be, and we've jammed a brick in just 10 centimeters away from the edge of the crowbar, and we start pushing down on the other end of the crowbar. If that distance is 10 centimeters, we get perfect equilibrium. If that distance is any smaller than 10 centimeters, or in this case 9.6 centimeters, whatever it is, if we can get a distance even smaller, that slightly increases the leverage of the 200 newtons and the 10G, but the crucial bit is it significantly decreases the leverage effect of the 500 G force. If, for instance, you drop your 10 centimeters down to 5 centimeters, it halves the moment that the 500 G force produces, which means the effect of the other forces is much more significant, and we actually get tilting in the direction we want to go. So the closer something is to the pivot, the smaller the moment of that force, which is how we can give this. Anything from 0 all the way up to, but not quite including, that edge case of 0.096 meters would be a small enough distance that we would get tilting. Now, you could produce the same effect if you wanted to. Instead of assuming equilibrium and solving an equation, you could say the net moment of the two forces on the right is greater than the moment of the force on the left. In other words, every single equals sign on this page you would see replaced by a greater than sign right up through the first three equations. At each point, we're saying the net force on the right multiplied by the various distances is larger than the net force on the left. And then when we rearrange a little bit and switch things around, the x in my final equation ends up on the left hand side because I've swapped around the sides of the equation. Then your greater than would have become a less than because you're writing it the other way around. And we have either 0.096 is greater than x, or x is less than 0.096. Now it's your turn to have a go at a question which is going to be similar. Again, it's an exam style question where we have a situation where we can think of equilibrium. The tension in the rope will change as the question goes by. So read carefully and make sure you reread as you go along. The first thing you want to get to grips with is creating a complete force diagram. Think carefully about what information the question gives in terms of the mass of the rod, the length of the rod, and therefore where the forces will be. There should be 3 forces acting on this, I believe, once you get everything sorted. Be careful, even if you manage to calculate the value of a force, don't write the value of the force on your force diagram if it might change later in the question. This is a great example of that. When we get to part C, the diagram changes, so you'll need a new diagram. They're adding a package of mass M to one side of the rod, and as a result the tension in the rope changes, so it's going to be a different value to what it was before. You'll need to go back through and work your equations once again. Pause this and have a go at this question. It's something like 12 marks, so you want to give yourself maybe 12 to 15 minutes. And if you get stuck, work it, play with it a bit, maybe go back and look at the early bits of the video to remind yourself how it works with force diagrams and moments. And when you're ready, unpause and I'll show you the mark scheme. Okay, so we can check what we've got for the very first part here. The 98 newtons is from the 10G. I tend to write 10G on my diagram to make it more obvious to myself. I've taken the mass of 10 multiplied by G. And then R is the normal reaction force at the pivot. And then we've got the tension pulling down. You get 3 marks in part B for, first of all, taking moments correctly, and secondly, for calculating the value of tension. So you get a mark for the moment equation, a mark for getting the moment equation correct, and then the final mark for the correct positive value of the tension. If you screw something up and get a negative or something and then just change it at the end, you're not going to get those final answer marks. But as long as you get everything right, there's 3 marks for that section. For the next bit, because they said the tension is doubled, we now know that T is equal to 2 times 24.5. So if you incorporate that into a new equation, you'll generate a new moment equation for 1 mark. If you get it correct, you get a 2nd mark. And if you successfully rearrange to find the mass, which comes to either 5/3 is acceptable or 1.67, which is probably preferred. Bear in mind we're doing mechanics, so we tend to think in terms of approximate values, usually to 2 or 3 significant figures. And then for the second part of part C, finding R, there's 3 marks again in this case, but all we need to look at here is the total of all the downwards forces, balancing out the total of the upwards forces. And in this case, there's only one upwards force, it's the normal reaction. We've got the downward forces of tension and the weight of the rod and the mg pulling down from the package that's been put on. The final part was asking what's the significance of saying the rod is uniform? How have you used that in your solution? And the answer is, well, we assumed that the center of mass was in the center of the rod. That's all we did. So we put the weight in the middle, basically, and that's sufficient. Our next exam question for you to try. This is a good example of a potentially tilting or about to tilt sort of situation. And to get a good feel for this, I recommend you get yourself a ruler and you rest it slightly over the edge of a table and look at what happens as you start pushing with gradually more and more force on the overhanging bit of the ruler. At a certain point, it's going to start to tilt. At the moment when it tilts, take a good look at which bit of the ladder, at which bit of the ruler is touching the table, because that is the only point where a normal reaction force will occur. If the ruler is just resting on the table, then technically there's a reaction force kind of spread out across the entire contact surface of the ruler. But if it's about to tilt, then the reaction force will occur only on the very edge, the point that it would pivot on if it actually tilted. So pause the video, have a go at this question, make sure you spend enough time constructing your force diagram and you read through and you make sure you get every single key bit of information. You've got your distances correct, you've got all the forces correct in the right places, and then you can start thinking about resolving forces and taking moments about any point that would be suitable. When you're ready, unpause and we'll go through the mark scheme. Here's the solutions for that last question. There's a mark for recognizing that the center of mass is 3 meters from the riverbank. And then if you take moments about the edge of the bank, you should end up finding that the distance x is 0.9. You'll notice there's an alternative on the right. You can get points for resolving forces correctly or for taking moments about any point, because there are various different ways to do this. Taking moments about the edge of the bank is useful because you never need to work out the value of r. But if you take moments about some other point, as long as you also work out the value of r in some way, for instance, resolving forces vertically, then that'll still work fine. You'll still get the marks. It might just be a slightly slower method, that's all. For part B, there's 2 marks again for taking moments. 1 mark for attempting to take moments, so it's clear that that's what you were doing, multiplying forces by distances, and the 2nd mark for getting that correct. So 50 times 2, there's a force times distance, and then 15 times 3, another force times distance, and m times 8 the equation they've got in there, if you look carefully, I think we'll find that the 8 is the distance, m is a mass, not a weight, but in each of the other cases, the 50 and the 15, they're both masses as well. So chances are your equation has 50g times 2, 15g times 3, and mg times 8, which will be a complete moment equation. But of course, if g is a factor of everything, then you could cancel that out. Once you get down to that point and you recognize that g cancels out, you will be able to simplify, rearrange, and you get 6.88 or 6.87, or 6 7/8 is also accepted for the number of kilograms that the object will be. For the next bit, they've asked you how you know, or how you've used the fact that the rod is uniform. It's the fact that the center of mass is at the center of the rod. And the final part is your modeling assumptions. In other words, taking off your maths hat and putting on your real life hat and asking yourself, well, okay, fair enough, this is the distance you might be able to walk out across the plank. How far would you really walk out in practice? How much do you trust the maths? And if you don't believe the maths is going to be 100% correct, why not? What is it about reality that makes it not quite perfectly accurately modeled by the mathematics? And these examples, the woman is a particle, the mass of the object they put on is a particle, or the plank is a rigid rod, these are all examples of modeling assumptions that we've made that may not be accurate. To try to illustrate this, I've got a picture for you. So instead of drawing a regular force diagram with just a point for the mass on the edge of the plank and a point for the person, well, what if we actually look at the true distance between the center of mass of the person and the center of mass of the object? And you'll notice that, I mean, you can try this yourself. If you try standing on the edge of a desk or something, your center of mass is probably not right on the edge of the desk. It's going to be some little way behind the edge of the desk. And it's the same if you've got a large heavy object and you put it down on a plank. Well, unless you've carefully positioned it so half of it is off the plank and half is on, the center of mass of the object is going to be some little way in from the edge. Now, obviously, if it's a 10-meter plank, that small discrepancy is going to have only a small effect, which is why it's normally safe to model smallish objects as if they're particles. But that's the kind of thing that the modeling assumptions need to take into account. The other one that I've not illustrated on here, because it's a little harder to draw, is a rigid rod suggests that it's not going to bend or flex. In reality, when you put your ruler out over the desk and start pushing on one end, depending on how flexible the ruler is, it might bend a little bit before it tilts. And if you've got a heavy object on one side, it almost certainly will bend. It's not just going to instantly tilt, it's going to have a point where the forces are not enough to make it tilt, but they are enough to make it bend. And that might be enough to make the poor lady fall off into the water, for instance. So it can change things. Okay, that's the end of the moments section of this. The last little portion of this video is going to be a bit of a recap and a refresher on what happens when we have forces acting at different angles. It's going to set us up well for the final section of the moments chapter. So we'll have another 5 minutes or so on that. So here's a force, a 10 Newton force, but the catch is it's not pulling the box directly sideways. It's pulling at a bit of an angle. Now, we're not going to worry about the other forces acting on this box at this moment. If it was actually sitting on a surface, then its own weight would be pulling down and there'd be a reaction force pushing it back up off the ground. There'd probably even be a frictional force resisting the pull of this 10 Newton force. But let's focus on the effect of this force for now. It's a 10 Newton force, but because it's at an angle, part of the 10 Newton force's effect is going to be horizontal, but part of it is going to be vertical. And in fact, because essentially it's a vector, we can break it apart. We can think of it as being a combination of a horizontal component and a vertical component. And if that 10 Newton force is effectively 10 as in the size of a vector that can be broken apart into horizontal and vertical pieces, then very often what we would prefer to do is to literally break it apart. Say, all right, how much of that 10 constitutes a sideways dragging effect and how much of it is a vertical lifting effect? And we can calculate that by noticing that what you're looking at here is just a right-angled triangle. So remember your SOHCAHTOA rules, the right-angled trigonometry results. We have sine theta, opposite over hypotenuse, cos theta, adjacent over hypotenuse, and tan theta, opposite over adjacent. Now, if you look carefully at this diagram, you'll notice that provided we're paying attention to the angle 30 degrees, then in this particular case, the opposite side is that light blue one, the vertical, the adjacent side is the purple one, and the hypotenuse is the one that we know the value of. That one is 10 newtons. So our equations become these. Sine of 30 is equal to the opposite side divided by 10. And cos is the other useful one, because the cos of 30 is the adjacent side divided by 10. One tiny little rearranging step allows us to say the adjacent side is equal to 10 times cos 30. And a very similar process will give you the opposite side, 10 times sine 30. In other words, if we have a force of 10 newtons and it's acting at an angle of 30 degrees to the horizontal, then the horizontal effect of that force will be 10 times cos 30. And you're going to find it helpful to shortcut this process. You don't want to have to think of it in terms of right angle triangles every time. You want this to be something that's quick and fluent. So you want to work towards the point where you can think of projecting directly downwards. Think of it like a shadow. Imagine looking down from above on this situation, and the purple arrow is effectively the shadow of the 10 Newton force. That's how much of the force is having a sideways effect. And therefore, cos of the angle is effectively the projection factor. It's what you multiply by to project in a particular direction. Now, it's a little weirder to think about what's happening vertically, but for a start, you could ask yourself, well, all right, if that's how I project horizontally, why don't I just use the same idea to project vertically? What about the 60 degrees that it would take to turn from the 10 Newton force direction that I've currently got all the way to the vertical? If I just keep rotating it another 60, it's going to be pointing straight upwards. So couldn't I do 10 times cos 60? And the answer is yeah, of course you could. But it turns out cos of 60 and sine of 30 are the same thing. In fact, the sine function and the cosine function are named specifically for that property, that sine of an angle is cosine of the complementary angle. It's the cosine of the angle that adds to that angle to make 90. In other words, sine of 10 is the same as cos of 80. Sine of 43 is the same as cos of 47. Sine of 89 is cos of 1, and so on. And in this case, sine of 30 and cos of 60 are the same thing. You can think of it in terms of the right angle triangle, if you like. The other acute angle in this triangle is 60 degrees. And if we look at the 60 degrees, then that would change which of these sides counts as the opposite and which counts as the adjacent. Now, it's worth pointing out that building fluency with this is probably one of the most important fundamental skills that you'll develop in mechanics, because it will come up within and as part of a whole bunch of other questions. Increasingly so as we start messing around with forces and moments in some of the later questions in the moments chapter, and also in chapter 7, which incorporates all sorts of information from this chapter and from chapter 5. And in chapter 5 itself, we'll be messing around with forces at all sorts of different angles, and it needs to be something you get quick and fluent with. So let's look one more time at how we can remember these results, and then you'll be able to go away and start building confidence and practice with it. And as you see them, hopefully it'll be something that starts to become second nature. So in general, if you've got a force F and an angle theta, which gives you the angle of the force relative to a particular direction, if you want to work out how much of that force is pointing in that direction, in this case horizontally to the right, you just multiply by cos theta. So that force F becomes F cos theta. And if you're turning the other way, if you're turning away from the angle rather than towards the angle or through the angle, you just use sine. And if it helps you to think, oh, the adjacent side, that's something to do with cos, the opposite side, that's something to do with sine, then great, because that works as well. The last thing I want to leave you with is a little bit of a sense check. So if you've actually got an angle, like 30 degrees, like we had in the last example, you'll find that 10 cos 30 is actually about 8.7 newtons, which looks about right for the diagram, and 10 sine 30 is only 5 newtons, and it made sense that one of these will be larger than the other. So there's a couple of examples here. I've got one for a very small angle, and cos of a very small angle is very close to 1. In other words, the horizontal component of the force will be very close to the same size as the force itself. Whereas sine of a small angle is close to 0. So if you've got only a very small angle that you're turning from the horizontal, then the force component which is acting vertically is going to be very small as well. And the flip thing happens if you've got an angle that's very close to 90, cos theta shrinks away, getting smaller and smaller, and sine theta gets closer and closer to 1. So if in doubt, or if you think you might have got them mixed up, try working out sine of your angle, cos of your angle, and see which one is the biggest, and you'll be able to quickly sense check which way around it ought to be. It's worth mentioning that this will still work if theta is not an acute angle. Maybe you're turning so that you're at an angle of 120 degrees. Generally, it's easier to just say, well, if I'm 120 degrees away from the rightwards horizontal, let's just think of it as 60 degrees away from the leftwards horizontal. Otherwise, it can feel a bit confusing. I mean, it will always work. Cos theta and sine theta just do their thing for any angle between 0 and 360 or beyond. But generally speaking, it makes sense to choose the direction that they're generally going in. If it's going up and to the right, like these three examples, theta is just going to be a nice, simple, positive acute angle. If it's going different directions, then you can just switch the direction of your horizontal or vertical arrows.